This is 2.5.1. రేపు క్లాస్ కున్నాను రేపు ఎగ్జామ్కి సరే. This is P is an ideal of a ring R. Suppose P is not finitely generated. P is not finitely generated and maximal among all ideals of R that are not finitely generated. Then P is prime. ఇక్కడ what happened is P is not finitely generated and is maximal among all ideals of R that are not finitely generated. Then P is prime. Then P is prime ideal. Show me. First of all, with that P is an ideal of a ring R. This is R is a ring. P is an ideal of a ring R. Then P is not a finitely generated. P is not a finitely generated. P is not finitely generated. P is not finitely generated and maximal among all ideals of R are not finite. And this is R, it is a between the maximal ideals are not reached the finitely generated. Then P is a prime. We know that. So first we are observed that P is not finitely generated, not finitely generated. Finitely generated. Meaning is, what is the finitely generated? Yesterday is the definition. Capital X is a set. The set is elements is a finite set x1, x2, xn. Is a finitely generated high is equal to generated by capital X. Is that there exists a scalars? It's a linear combination R1 x1 plus R2 x2 plus up to so on plus Rn xn. This is a finitely generated. But this theorem is not finitely generated. P is not equal, not finitely generated by I is equal to R. I is equal to R and P is not finitely generated. So that A comma B belongs to R or such that this is such that AB belongs to P. You show me A belongs to P or B belongs to P, that P is prime ideal. That P is prime ideal. So what happened is, you show this is AB belongs to P, we take and show, we have to prove that A belongs to P or B belongs to P either, then P is prime ideal. Suppose I am taking, this is suppose given, and it is suppose B does not belongs to P, we have to prove A belongs to P. So B does not belongs to P, P is a ideal. This is R is a ring, the P, so RA is a generated by single element. It is also ideal. This generated by single element RA is also. P is also ideal. RA is also ideals of R. And two ideals, addition is also ideal. P plus RA. Suppose B does not belongs to P, we taken, then what happened? P plus RA is an ideal of R. An ideal of, so ideal of R. Ideal of R. So which is properly contained in P, which is properly, and that is P plus RA is a ideal of R properly contained P. This is a properly contained P. Okay. But maximality of P, it falls up. So what happened is, this is P is not generated, but P plus RA finitely generated. So, but P plus RA is finitely generated. Finitely generated. So this is finitely generated. So it's a clear now. This is Okay, now P plus RA is a finitely generated. P plus RA is a finitely generated is clearly now this is so it's a taken P plus RA finitely generated. So what is a P plus RA finitely generated is called is so now so it is a P plus RA finitely generated is meaning P is a ideal, R is RA is also ideal. This summation of two ideals is also ideal of a ring R is a finitely generated can be pick up. This is P1 plus R1 of A. So small P1 element of capital P. R1 of belongs to A. So next to small P2, this is small P2 plus small P2 R2 of A up to so on small Pn plus Rn of A. This is a small P1, small P2, small Pn is belongs to capital P. Small R1, R2, R2, Rn is belongs to small Ri is belongs to capital R. Small Pi, this is a belongs to capital P. Okay. So this is a small a is a generated element also. So it is this is a set is small P1 plus R1 of A. Okay. Up to so on. This is Pn of plus Rn of small a like this. Capital I is equal to one ideal, other take ideal. Small x is belongs to capital R and first starting ideal. I is not generated such that XA is the element of capital. This is XAL. So I is not generated, the I is equal to formation. X belongs to R, XA belongs to P. I is an ideal of R, I is an ideal of R, and ideal of R, ideal of R, and I is an ideal, R is a ring, I is an ideal of R, and also P subset, I contain subset R equal to P. B belongs to P. Connect what now? Now taking B belongs to I. We taking B is a belongs to P. Since B belongs to Y are in I is means BA belongs to P and upload. This is also B belongs to I. So it is same thing. Also that B does not belongs to P. So high is properly contain P. And therefore high is properly contain P. This is must be. I is properly contain and only properly contain P. I is properly contain P. Again the maximality of P. This is the maximality of P. Already it is a given statement. Maximal of along maximal among all of ideals are not finitely generated. Maximal of I is generated finitely generated. Suppose maximal again maximal of P, I is a generated finite. Suppose I is equal to finitely generated capital X. Capital X is equal to what now in small x1 up to small n. It is a taken. So again, now it is claimed that P is a finitely generated. So finite set. What is the P finitely generated? P is a finitely generated finite set is small p1, small p2 up to small pn, x1a, x2 of a up to son xn of a. Xm is taken small m, xm of a, which is a contradiction. Since P is not a finitely generated, since that what is the element
Sir, sir, your voice is not audible, sir. Hello, sir. Sir, your voice is not audible, sir. Sir, sir, you muted yourself, sir. Hello, sir. Hello, sir. Sir, Hello, sir. Sir, 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 sir. Sir, unmute yourself, sir. Sir, I'm not able to listen, sir. Sir,
Hello, speak.
Sir. Hello, sir. Hello, sir. Voice is not available, sir.
Hello,
Yes, sir.
hello.
Yes, sir.
Uh, Teja is available. Is listen to me. Am I speak? Hello,
Yes, sir. Yes, sir.
hello,
Yes, sir.
hello,
Yes, sir.
hello,
Yes, sir.
hello.
Yes, sir. Audible,
P
sir.
Teja. Hello, P Teja.
Yes, sir. Sir,
Teja.
audible, sir.
Hello.
Yes, sir.
Hello, Teja. Hello. Okay. Hello, Teja.
Yes, sir.
Yes. No. So A not equal to 0 or 0 not equal to a non-unit element is belongs to P can be written as product of finite number of prime element. So this is, so A is non-zero element of non-unit element, capital P is a prime ideal. So this is a non-unit element of prime element is a product of finite number of prime elements. So say A is equal to small p1, small p2 up to small pn. So this is a small pn, where pi is prime element. Pi is prime element. This is pi is prime element. So p1 is a prime element, p2 is prime element, pn is a prime element. Small a is equal to also. This is small a is equal to product of finite p1, p2 up to pn. This belongs to capital P, prime ideal. So since P is a prime ideal, it follows that so Pi is belongs to capital P. Pi is belongs to P. So Pi is belongs to P. We have to prove is completed. Unit factorization domain. Every non-prime ideal contains every prime. This is a proof. Every non-zero prime ideal. So it contains prime element. Pi is a prime element. Conversely, we have to show me D is unit factorization domain. So we taken conversely part. This is conversely. What is the conversely we taken? Let. This is called. Suppose every non-zero prime ideal in D contains a prime element. Suppose every non-zero prime ideal contains primordial D contains a prime element to show that T be the set of, to show that D is a unique factorization domain. But let T be the set of all product of finite number of prime elements in D. So what we can, according to definition, let T is equal to be the set of all finite number of product P1, P2. So finite be the set of all finite number of product of prime elements. Prime elements in D is in D. We shall prove that T is structured multiplicative closed set. Then T is a prove that T is a structured multiplicatively closed set. T is a structured multiplicatively closed set is a structured. This is structured multiplicatively closed set. This structured multiplicatively closed set in D. Clearly, T is clearly T is multiplicatively closed. This is a closure property. A comma B belongs to D, capital D. A comma B belongs to capital D, such that AB belongs to T. It is a closure property. T. We can write AB is equal to T. What is the T? The T is meaning the set of all product of prime elements. This is AB belongs to T. Then T is equal to AB is equal to product of prime elements are there. Small p1, small p2 up to small pn. So where is the pi is prime element. This is prime element. This is a prime element also. Now pi is being a prime, it should be divided either AB. P divides A. So what is a divides AB, or meaning the prime element pi is a divides AB, or implies P divides of I A or P divides of B. It is taken. So P divides of B. It's a clear. Now either A or B. So divides P divides of A. Suppose is taken Pi divides of A. So then what is the divide? A is equal to formula, division formula, Pi into small ai. Okay. Where is the ai is belongs to? Capital D. D is a ring. Got it. Therefore, so according to definition, Pi ai. So what is now? AB is equal to already. So Pi ai into B. So Pi ai. This is AB product. The AB is equal. AB is left side product, right side product. This is called as Pi ai B. It's a left side. AB is equal to what is AB? Product of finite number elements P1, P2 up to so on This is a Pn. In middle of the term, it is a Pi, it is there. So it is a Pn. It is the middle of the term is Pi. And what happened is, so clearly Pi Ai B is equal small p1, small p2 up to one, middle is Pi into Pn product. So one Pi is cancellation. Suppose what happened is called is A high of B is equal to, what is the element is, one element is left and P1 element is king. So this is P1 of AB is equal to, what happened? This is AB is equal to P1, P2 up to so on Pn. So P1 element is cancelled. That is called is A1 of B. A1 of B is equal to P2, P3 up to so on. A1 of B is equal to P2, P3 up to so on Pn. So now he is induction on N to prove that A1 or B. So on induction A1 or B, this is a part T in T. This is a T. Therefore, either A or B in T. Thus, T is structured multiplicatively positive set in D. So already you know R over of T. R over of T is means, so this is called as a complement of T. R over of T is a union of prime ideals of D. Is a union of prime ideals of D. So now to be A is a non-zero unit element D. So therefore A does not belongs to of T. Therefore A belongs to R over of T. So therefore there exists a prime ideal P such that A belongs to P. E are substituted for R over of T. Therefore by hypothesis that prime ideal sub should be contains a prime element P will not be in T. This is a contraction. So therefore A is a belongs to of T. Therefore, every non-zero non-unit element D can be written as product of finite number of prime elements. The uniqueness of the product of the proved in way in the way. So called therefore 100% you can write here. This is called T is a structured multiplicative closure set. Then D is a must be unique factorization domain. So it's a clear this top. Again one definition. This is the definition is called is radical. So the radical of phi. So this is a definition is, so the radical of phi. So the radical of phi is called is that high R is a ring. I is an ideal of R. R is a ring. I is an ideal of ring R. The radical of phi. The radical. This is the radical of phi. The radical of phi. So it is defined as, this is the defined as R of phi, the radical of R of phi. The set of all x belongs to R such that x power of n is belongs to capital I. So where for some n greater than 0, where is x belongs to R, I is an ideal of a ring R. So the radical of phi is defined as R of phi, small r of phi. The set of x belongs to R such that x power of n belongs to capital I for some n greater than 0. The radical of always is ideal. So the radical of any ideal I is always ideal. So it is a ideal is also. Now, this is also the R of I. This is R of I is always is an ideal. So is of radical of any ideal I is always ideal. Any ideal of is I is always ideal. This is a formation. So it is also for some, and this is belongs to x belongs to capital R such that x power of n is belongs to capital I. Any ideal in this formation is always ideal also. Suppose example, x power of n into y power of m is belongs to capital I. So x plus y is whole power of n plus m is equal to, the expansion is always belongs to capital I. This is a closure property with respect to addition. So Rx is also belongs to capital I. So is belongs to capital I for all small r belongs to R. So according to this is also ideal definition. It is also ideal. Now it is next is let I be a theorem. Let I be an ideal of a ring R. Then radical of I precisely the intersection of all prime ideals of R containing I. So this is now I be an ideal of an ideal of, this is an ideal of I be an ideal of a ring or then radical of I precisely the intersection of the prime ideals of or containing I. Intersection of prime ideals of containing I. This is called this. So it is proof is First we are observe that no prime ideal of containing I. First we observe that no. First we are observe that. First we observe that. We observe. We observe that. First we know observe that a no containing no prime ideal. No prime ideal of no prime ideal containing I. If and only if I is equal to R. I is equal to R. No containing is I is equal by previous theorem. So the radical of I, so it means the radical of I, R of I is equal to R. Therefore, we assume that I is a proper ideal. We have to prove that R of I, we have to prove that R radical of I, the intersection of. So this is the P, the set of all intersection such that P is a prime ideal. And so I subset R equal to P. So this is called is R of I is equal to proof. The radical of I, so the radical of I is means radical of I is means it is a meaning the intersection of this is intersection of the set of all ideals P. Where is the P is a prime ideal. This is a P is a prime ideal. P is a prime ideal. This is a prime ideal. So prime ideal. And also what about P? I subset R equal P subset R equal to I. Sorry, I subset R equal to P. So I P is contains R I. So P is contains C I. So we have to prove this is called is now let x belongs to R, x belongs to I is a positive integer n. So x belongs to R is taken. So if x belongs to radical of I, what is the radical of I definition? Then x is equal to formation. Compulsory therefore in a positive integer n. This is the formation x power of n belongs to cap P. In fact, what is the definition? R over of I is equal to such that x is belongs to R, such that x power of n belongs to capital I. This is the where is the I is ideal. So what happened? X is belongs to radical of R over of I. Any ideal P we taken. This is the formation R over of I in power n positive integer. N belongs to positive integer. Is the x power of n belongs to P. So x power of n belongs. Where is the x belongs to P? Every prime ideal P containing I. X is belongs to P. So hence x is belongs to P is a so every prime ideal containing P. So every prime ideal is containing P. So every prime ideal containing P. So containing I. So this is every prime ideal is containing P. This is I subset R equal to P definition. So containing P. So otherwise, other hand, suppose this is a x belongs to R or I. Other hands is x does not belongs to other hands. This is x does not belongs to other hands. This is x does not belongs to R over of radical of I. So what happened in this situation? This is compulsory x power of n does not belongs to I. So for every n is greater than 0. So put in the form s is equal to the set of all x power of n such that n is a positive integer. N belongs to positive integer. N is positive integer. So the s is a multiplicatively closed set and R in R. So S is a multiplicatively closed set in R. Therefore, R and S intersection is designed. R and intersection is designed. Sorry, I and S is a disjoint intersection. S is a multiplicatively closed set in R. I and intersection S. S is a multiplicatively closed set in R. I intersection of S is always is a design. So it's a design. There exists a prime ideal P such that already it is a theorem. I subset R equal to P intersection of S is equal to also design. So that is, so it is called is x power of n does not belongs to P. X power of n for all n greater than P. So called therefore, so in particular, x does not belongs to P and I subset R equal to P. So he complete. And this is a radical of I. X is a belongs to radical of I. The theorem is power also. Is the case is proof x does not belongs to R over of I. Please also continue with the proof also. It is this is a prime address containing her. Now it is clearly. So this is it is now next to 2.5.12. This is a totally 9.9. Sorry, following ons. For any ideal, I and J are ring are the following rules. So I and J are two ideals of a ring or we have to follow up to 1, 2, 3 up to 7, 9. So following rules are there. First part is I subset are equal to I, R over of I containing I, R over of I contained I. So R over of I contained I, R over of I is contained I. This is a first one. This is the first part is theorem. Uh, R over of radical of I is contained I. So, so this is R over of I contained in the trivially. This is R over of I. So R over of I. So every this is I is. So what is the definition is called is R is a ring, I is ideal of a ring, or R over of I is equal to. The definition is X is belongs to R such that X belongs to X power of n belongs to I for some n greater than 0. This is the formation. The radical extension of R over of I is always is contain the smallest ideal. The R over of radical constant, the smallest ideal containing I. Therefore, the radical constants are R over of I according to trivially. So, so it is by previous part is also now. Now second part is the radical of I is always is R over. Yes, according to definition, this is exactly this is R over of I structure is R over of I is a structure is the set of all x's belongs to R such that x power of n belongs to I, n is positive integer. Next to R over of I is meaning. So we can do apply the same. Some taken y belongs to half R such that this is y power of n is belongs to this is of R over of I. So according to R over of I is equal to also the formation. This is R over of I in the formation is called is same is y belongs to R such that so y power of n belongs to capital I. This is a formation is equal to in structure of R over of I. R over of I is equal. This is second. Now third. What is the third is R over of ij is equal to R over of I intersection j. Okay. Is equal to R over of I intersection R over of j. This is the radical of ij is equal to radical of I intersection j is equal to radical of I intersection radical of j. Radical of j. So this is called is now. So in fact that P is a primordial. This is the third part. P is a primordial of a ring R. Is a P is a R is a ring. P is a primordial. This is the primordial of a ring R. I is subset R equal to P if and only if R over of I is every R over of I P primordial R over of I contained in P. So this is the product. I is equal from this is next to I j. This is the product of two ideals is subset R equal to P. This is found only if I subset R equal to P or J subset R equal to P. That is called as P is a primordial. What is the primordial definition? So what is R is a ring, P is a primordial. There exist two ideals A comma B such that A B subset R equal to P and therefore original ideal P. There exist two ideals A comma B. A B subset R equal to P. This implies A subset R equal to capital P or B subset R equal to capital P. Then P is also primordial definition. So actually primordial definition, element to definition, small a b belongs to product, small a b belongs to capital P ideal, is implies a belongs to capital P or either B belongs to P. That is a primordial definition. Other hand definition, P is an ideal of a ring is said to be primordial. There exist two ideals A comma B such that A B subset R equal to P, then either A subset R equal to P or B subset R equal to P, then P is called as a primordial of a ring or same. Same concept we have to do. I subset r equal to p. This is if and only if must be the radical of a radical ideal of the radical of I subset r equal to p. Same I in plus it you can do. So I j, this is subset r equal to p. Where is I comma j are two ideals? P is a original ideal. That is a prime ideal definition is if and only if I subset r equal to p or either j subset r equal to p. Since p is a prime ideal. Since p is a prime ideal. So this is a piece high subset r equal to p అయినప్పుడు ఏముంది radical of I. So must be radical of j, radical of ij అంటే radical of ij ఏమవుతుంది, radical of ij subset r equal to p అవుతుంది. నెక్స్ట్ radical of, so radical of I, so radical of I subset r equal to p and radical of j subset r equal to p. Intersection is also what happened is separate intersection. Now again this is if and only if, this is if and only I intersection j is subset r equal to p. So the radical of I intersection j subset r equal to like that. Radical of I intersection j. So that is a meaning. This is a meaning is if and only totally. I j is a actually first one is I subset r equal to p. Therefore, if and only if radical of I sub containing subset r equal to p. Next to I in plus lo j written. Ij is subset r equal to p prime ideal definition if and only if I subset r equal to p or so j subset r equal to p. Next to this if and only if r plus lo radical వచ్చినప్పుడు therefore I intersection j is subset r equal to p. I intersection j subset r equal to p. This is it. This I intersection j subset r equal to అయినప్పుడు therefore radical of I intersection j is equal to the radical of I, the radical of I and intersection, and therefore the radical of I intersection j is called radical of I intersection the radical of j. This is a second part. Last part came therefore is equal to same, and it is a continuously radical of I intersection j I intersection j is equal to the radical of I intersection the radical of I intersection the radical of j is equal to same the second part nunchi appu first part. Therefore the radical of ij, this is a radical of ij, so it's called this. So once again chudandi, I subset r equal to, this is called this what is I subset r equal to p if and only if p is a prime ideal, I is a ideal అయితే the radical of I subset r equal to p. So I in plus j written. Therefore I j is a subset r equal to p if and p is a prime ideal definition I subset r equal to p or j subset r equal to p. This is if and only if I intersection j, so I intersection j subset r equal to p. ఇక్కడ నుండి therefore radical of I intersection j వస్తుంది ఈక్వల్, ఇక్కడ నుండి ఏమొస్తుంది radical of I intersection radical of j. So ఇక్కడ నుండి ఏమొస్తుంది the radical of ij, the radical of ij. It's a clear this part. So it is so is naturally is the fourth part. I subset r equal to j. I subset r equal to j implies radical of I subset r equal to radical of j. ఎక్కడి నుంచి వస్తుంది సార్ అంటే like that. By fourth I subset r equal to p if and only radical of I subset r equal to p. So therefore ఇక్కడ I plus లో j తీసుకోండి. Therefore radical of I radical of j, radical of j. So if I, so it is a fourth part. Fifth one. So what is the fifth one is radical of I is equal to r if and only if I is equal to r. I is equal to r. So this is I is equal to r is means now you can write here this is small I belongs to I right here if and only if I belongs to ఏమైతే కంపల్సరీ radical of I. So it is called as, therefore radical of I is equal to, so first part radical of I is equal to I is equal to R. So this part now you can do right here, I is equal to R. So the radical of I is equal to R is equal to if and only if I is equal to R. I plus R but I is equal to R. So it is, so fifth one. So sixth, radical of I plus J is equal to, this is radical of I plus radical of J. So this part is, so it is now. So first one, every ideal is I subset are equal to radical of I. Okay. ఎందుకంటే therefore every radical of I is a ideal of any ideal I. And same J subset are equal to radical of J. Radical of J is an ideal of any ideal J. And not directly radical J is a ideal of a ring. And I is a ideal of a ring or J is a ideal of a ring or those left side addition. Left side addition and what happened? I plus J is a subset or equal to radical of I plus radical of J. Radical of J. So it is radical of J. It is called now. దీనికి బోత్ సైడ్ రాడికల్ అప్రోచ్ అండి. అంటే ఏమొచ్చింది, హై Okay. Hello. Is clear? Listen. Hello.
Yes, sir.
No. Okay. The radical extension similarly way. It is a seventh. High is a prime. So R of radical of I power of n is equal to high. I power phi is a prime. Radical of I is equal to high. Uh, so it is a. This is called is. Now this is a seventh is. What is I is a prime. I is a prime ideal. E is prime ideal like that. Implies R over of radical of I power of n is equal to I. Therefore, n greater than 0. So it is a the third one R over of ij is equal R over of I intersection j is equal to R over of I intersection R over of j. R over of j is equal to I put chain. We like that. R over of I into I. This is a high square is equal to R over of I intersection R over of j. How like that? R over of radical of I square is equal to radical of I. Radical of I. Radical of I is equal to the radical of I is equal to also what happened is R over of radical of I is equal to also R of I square is equal to radical of I is equal to I. This we take a radical of I is equal to I. So it is the radical of I is equal to I. I square is equal to radical of I is equal to I this one. Same thing. Radical of I cube is equal to also is I. R over of. Okay. Now, so similarly, radical of I power of n is equal to also I. N is positive integer. Next to eighth one. I plus j is equal to R comaximal ideals. So if and only if R over of I plus R over of j is equal to R is shown. I plus j is equal to addition if and only. So it is taken what no. So it is a taken. This is from fifth to what is a fifth to R over of I is equal to R. If and only if I is equal to R. Both side addition R over of I is equal to R over of I plus R. So we have to I in plus fifth, I in plus j, we have put them, I in plus j, we are put them. So I in j in put them, this is called is R over of I plus j is equal to R. If and only if I plus j is equal to R. What is R over of I plus j is equal to? Already we know R over of I plus j is equal to is also the R over of I, R over of j. So R over of I plus j and I plus j is equal to R over of I. So the R over of I plus j is equal to, so it is called this. So R over of I, radical of I is equal to R if and only if I is equal to R. I am taking I in plus j with j I plus j. R over of I plus j is equal to R. Also if and only if I plus j is equal to R. What what is R over of I plus j is equal to R over plus j. So therefore R over of I plus j, R over of I plus R over of j is equal to R over of I plus j is equal to, so R over of I plus j is equal to R over of I plus R over of j is equal to r. Therefore, indirectly ఏమవుతుంది r over of I plus r over of j is equal to r. If and only if I plus j is equal to r. This is a eighth condition. So eighth condition. So ninth condition. What happened is ninth condition. So finally we like that I subset r equal to j. He clearly r over of j is quotient ring or r of I subset r equal to r over of j is quotient of I. So like that. This is called is r over of I subset r equal to j. Clearly r over of j is quotient ring in subset r equal to r over of j over of I. This is called is. Let quotient ring element is x plus I is belongs to r over of the radical of j over of I. So x plus I is a whole double dash is belongs to j over of I. సో ఎక్స్ అంటే టూ టైమ్స్ అంటే ప్రోడక్ట్ ఏమవుతుంది ఎక్స్ డబల్ డాష్ ప్లస్ ఐ అవుతుంది దట్ ఎలిమెంట్ ఈజ్ ఈక్వల్ టు ఏ ప్లస్ ఐ తీసుకున్నాను చూస్ ఏ బిలాంగ్స్ టు జే సో అప్పుడు ఎక్స్ డబల్ డాష్ మైనస్ ఏ ఓకే ఈజ్ ఈక్వల్ టు ద వాట్ ఇస్ ద ఎలిమెంట్ ఎక్స్ డబల్ డాష్ ఆఫ్ ప్లస్ ఐ ఈజ్ ఈక్వల్ టు ఏ ప్లస్ ఏ ఐడియల్ సబ్ట్రాక్షన్ ఎక్స్ డబల్ డాష్ మైనస్ ఏ బిలాంగ్స్ టు హై. So this is high and a is also belongs to j and therefore x double dash of minus a belongs to I intersection j. So called therefore x double dash of belongs to j is also therefore x double dash belongs to j and x double dash is belongs to r over of j. Therefore r over of j over of I is equal to r over of j over of I. So this is a ninth part is completed. So it is a clearly the definition is okay. Next in topic is a discussion is called is maximal ideal topic or new topic. So it is now maximal ideal topic. Tomorrow we'll continue. This is maximal ideal. Now maximal and Jacobian radical also. Now a very small topic. Okay, I'm this is leave this class. I'm end of the class now.